So optimization now, moving to optimization mode. So I'm going to go back here to my case without output and go to the options screen and then change to optimization mode. In terms of inputs, it's very similar to parametric mode. And in some ways, you can think of parametric mode as a sort of brute force analysis that does all possible combinations across categories where you've selected multiple options. But as we said, that can blow up. In optimization mode, you have somewhat more, it's not going to blow up as fast. So you can select multiple options in a number of categories, and then BOPT will, in optimization mode, use a search technique to efficiently find the most cost-effective building designs, whereas parametric would give you sort of the same results, but by a very much brute force approach in terms of the number of simulations that would be run. So you can select multiple options in categories. Some categories that may not make sense to include in an optimization. So, for example, you might not, for an individual building, you may know what the orientation is, the direction that the front of the building faces, and you may not have the flexibility in your design process to change that orientation. Similarly, you may know that you are in fact going to or not going to have neighbors. Other items, especially here, some of these things, the heating set point, which controls the furnace operation, you may know that if you're in a cold climate, if I select a range of heating set points, I sort of know that in terms of energy efficiency results and minimizing cost, that the lowest set point is likely to come out to be the optimum. So I may be wasting a number of simulations for higher set points. So you want to choose what you optimize over in an intelligent fashion, both to not waste simulations on things that aren't going to give you useful information results. And also, you still want to be somewhat judicious. There's the categories and the options in BOPT. There's like maybe 500 available options. If you swiped every category here and asked the program to do that, for one thing, there's a lot of categories, for example, in the wall insulation that, if you're in a cold climate, you know that some of these poorly insulated options are not of interest. Or if you're in a mild climate, maybe some of the more extreme options are not of interest. So that's a matter of engineering judgment. So now I'm going to go to just a little bit of background information on optimization. So we refer to the upper left graph that Scott was showing and that we're going to see more on the BOPT output screen is in a format here where we are looking to find cost optimal or minimum cash flow designs between the base case and zero energy. So if we start here on the y-axis, we have sort of energy-related cash flow being, and there are various choices of what you display on the y-axis and actually what you optimize over, and Scott will cover some of that, but a basic one from the homeowner's perspective is utility bills plus the incremental or the mortgage increment to pay for additional efficiency measures. So energy-related cash flow on the y-axis, x-axis is, again, there are some choices that you have about what's displayed, but typically energy savings relative to a base situation. So in the unimproved building, we have not made any investments and don't have any mortgage payments for energy efficiency. We just have the original or initial utility bills. As we improve the building, the utility bills drop, and we can start with some very low cost or no cost measures, but then we start paying in a new construction context, typically increasing the mortgage by an increment to pay for efficiency. As we continue on, we have the mortgage rate now going up at a greater rate than initially relative to the utility bill savings, because we're having to dip deeper into the pool of efficiency measures. We have diminishing returns, less bang for our buck. And if we were to continue to do efficiency beyond, to try to achieve high percent savings, the cash flow curve, the sum of the utility bills and the mortgage payments, starts to increase steeply because we're really into a region of diminishing returns. And maybe we're using some of those options that are not very appropriate for the climate that we're in, but we've used as many of the good options as we have. So that starts going up steeply if we're trying to push to higher savings with efficiency. BOPT always is comparing the marginal cost, the cost of the next increment of energy savings from efficiency, to the cost of producing energy with PV. And at some point, the efficiency savings become more costly and less cost optimal than using PV. And then in a simple version of this, we just are adding larger and larger PV arrays, potentially getting to net zero energy. So at the end, as you recall, we started out with utility bills being the energy-related cost. When we're done, in a simple conceptual sense, we've eliminated utility bills, and we have mortgage payments, upfront purchase of efficiency, and PV. So that's the conceptual path to zero net energy. Now, this is just a sort of hand-drawn concept. We'll see similar results from BOPT, but the fact is, while we know the curve is going to have a shape similar to this, we don't know exactly what the curve is because there's a wide range of building designs representing different combinations of efficiency measures that have different levels of energy savings for each design, and then associated costs in terms of utility bills and efficiency measure costs built into those. What we would like to find is the lower boundary of this cloud of points, so that depending on what one's goal is in terms of energy saving, however much energy saving or what level of efficiency we want to operate at, we assume that we'd like to do that most cost effectively at a minimum energy-related cash flow. So this is our objective. How to do that with the tool, this is an example of an optimization result from BOPT with similar values on the axis, and each point here representing a different building design. So again, we're trying to find the lower boundary. The question is, as we do these simulations, as I mentioned, optimization is an efficient way compared to parametrics. Parametrics would run all possible combinations. The optimization uses a search technique to fewer than all possible combinations. The question is, was it effective at finding the lowest cost solutions? Now, we did a test at one point where we did some distributed computing with like 50 computers over a long weekend, and we did 750,000 simulations represented by the gray cloud, So those are all the possible combinations. That would be a parametric run. For not 500 options, we selected 75 options here, but we did all combinations of those 75 options. The good news is that we don't see any gray points significantly below the curve defined by BOPT, which used about 1,000 times fewer simulations. And so depending on what simulation engine you're using, if you're running optimizations, and you know, as I mentioned, you might be doing 1,500 or 2,000 building design evaluations in an optimization, depending on how many options you selected on the input screen. But this is a matter of some hours of computational time. You may want to do optimizations overnight, but at least you don't have to have 50 computers running for 3 or 4 days to get this result for a given building analysis in a particular climate. Okay, so now having described the optimization input, Scott is going to talk more about what's available in terms of information on the output screen.
Thanks, Craig. So what I'm going to actually do is I'm going to open up one of our sample project files again that includes results. An optimization, depending on if you use DO2 or Energy Plus, could take anywhere. DO2 optimization maybe takes around, well, it depends how fast your computer is, how many processors you have, but several hours, I guess I would say, maybe 2 to 4 hours. Energy Plus longer because each simulation takes longer. So here we have a project file where we ran results in both Chicago and Phoenix, in both the DO2 and the Energy Plus simulation engines. Just quickly look at the option screen. You can get a sense of sort of how many options we selected across the different categories. You know, there's obviously a lot of options that we didn't select, but at the same time, if you were to do the math and multiply all these options out in terms of the possible combinations, it is a lot of combinations. So the optimization in only taking several hours is quite a bit more efficient than that. So let me go to the output screen here. So this is a fairly typical optimization result that we would get in BOPT. Again, on the y-axis, we have our annualized energy-related costs, which, as Craig talked about, is the utility bill costs plus the increment of mortgage payments to cover the technology improvements. So we start off at just utility bills here. We employ a lot of efficiency that in this situation is very cost effective in that it's lowering utility bills faster than it's increasing the mortgage payments. So on the y-axis we're going down. We start to go up a little bit, and then there's this sort of straight slope where we're employing more and more PV. You can choose, actually I should have shown this beforehand, but let me go back for a second and create a new case. So now I've got a case just with the same inputs but no output. At the time when you choose to run the optimization, on the run dialog there's actually a more button here. You've got a few different choices available to you. You can choose the y-axis metric and x-axis metric that you optimize over. And at the moment, there's only a few different options. We're constantly adding more. So, for example, you get optimized over site energy instead of source energy. And the last choice is actually a stopping constraint for the optimization. Do you want to stop at, let's say, trying to get to zero net energy? Do you want the optimization to only go to 30% and then stop? So this is a way to save some simulations if you're not interested in the entire curve all the way from 0% energy savings to zero net energy. You can choose some other metric. You could choose the min cost, the sort of lowest point on the curve, the most economical point. So in the optimizations that we have in our sample files here, we actually chose to stop at PV end. And that's important for mentioning because if I go back to this optimization result, what you see here is that we employed PV up to a certain amount, and if I scroll down here, I can see that that amount was 8 kW. So we allowed BF to put in up to 8 kW of PV, and we constrained it. We didn't let it put in more than perhaps could fit on the roof. If we had not chosen to tell the optimization to stop at the end of PV, you actually would have got this tail off here because we're still not at zero net energy. We're only at about 83% energy savings. So there would have been this tail of efficiency that is more expensive than PV. And so perhaps you are interested in that efficiency tail, but perhaps you're not. So you can just keep in mind that you can choose various points at which to stop the optimization. It's pretty interesting to look at. Craig was talking a little bit about how well the sequential search works. You know, for a 30% building, so I'm going to click this drop down here and select 30% building. So that's about $1,700 per year of annualized energy-related costs. What's interesting to point out is that if you just draw a line up, you could be all the way up here. You know, you could have easily defined a number of other buildings, and there's an optimization, so we don't show the entire cloud of combinations. We don't run all those buildings. But there are at least technologies all the way up to here that would have also saved 30% energy savings at over $1,000 more a year. So this is a little bit demonstrating the why having the sequential search optimization in BF is very useful, because it's easy to come up with a design that saves your target energy savings, but trying to do so in a cost-optimal manner can be very challenging. If you right-click on this graph, so at the moment we're showing we actually optimized over this y-axis and x-axis metric, but you can actually still choose to display other metrics after you run the optimization. So for example, on the x-axis, I can now choose to, instead of look at source energy savings in percent terms, I could look at site energy savings for all these different building designs. You see that it gives you a fairly similar curve, but there are definitely gray points that are below the curve now, because all we're doing is redisplaying the points. So keep in mind that while you can display other metrics based on the simulations that you ran optimized for a different metric, these are not results that are optimized for this new metric. If you actually reran these simulations and optimized for this metric, you could get a slightly different curve than what you're seeing here. Or I should say you would get, we know you would get, because there are points again that fell below this curve line that was based on source energy savings. But so there is a lot of flexibility to be able to display the results over different metrics. And we are adding, like I said, quite a few metrics to be up. Lastly, I'll just mention that you can also, if you use your mouse wheel, you can zoom in on the data. So for example, if you want to try to find a minimum point here, you can zoom in. You can click a box, drag a box, and select multiple points. And then for those selected points, get the energy results by end use, as well as the various technologies that made up those different designs.
So this is where the display on the right-hand graph helps you understand what's in a given design.
That's correct. So if you're trying to look at maybe you're interested in a couple, or you weren't quite sure what building package you wanted to put in, but you just knew that you wanted it to be, you know, down near the bottom of this graph, you could select several points, and then on the right-hand screen, you can very quickly get a sense of what is different between these different building designs in terms of the different packages that you might want to be interested in building. So for example, we're seeing a couple of different air conditioners show up here, dehumidifier as well, etc. So we try to, BF stores all of the information, and it's quite a lot of information associated with every point here on this curve, so that for any point that you click on, you can get the building design, the cost information, the end use, information, energy, utility bills, it's all there in BIOP. Alternatively to using the interface in BIOP, you can also, it does have what it calls a detailed report, so that you can put all of this information and more into a CSV, sort of an Excel file that you can post-process information with yourself if you want to. So that's a flavor of what you can do once you have your results from your optimization in terms of hunting around and trying to find out what packages you may be interested in, exploring why you're getting the results that you do. So everything we've done to date, and I'll mention one other thing, which is, so let's say I picked again the minimum point on the curve, and so that actually shows up right here. You can go straight to it with this drop down. Let's say you wanted to do maybe a little bit of sensitivity analysis around this point. You know, BIOP ran a lot of points, but you're interested in knowing how this point is sensitive to some of the different technologies. One thing you can do is, for the point you have selected, there's a button here that says Export Selected Point to New Case. And if you click that, it's actually going to take the technologies that made up this point and give you a new case. And I'll go ahead and click it. It'll give you a new case where that point is, or that case is now in design mode, and that's the only point in that case. So you have the technologies from that point, and you can now right-click on it and do some new designs, or you can run a parametric based off of it. So it's a very quick way to, you know, you started with input, you ran some simulations, you got some output, and maybe you want to go back and get back to the input and run some more outputs based on that. So it lets you quickly grab that information and put it back to the input side of things.